This is 4-1 trying congruence and transformations. Let's take a look at the warm-up problem. Start by graphing both the original pre-image points and the new image, the transformed image. Notice what happened here. The A, B, and C stayed in the same position. It was just slid over to the right. Exactly 1, 2, 3, 4, 5, 6 units to the right. So let's look how to write that in a map. So up above I've written that xy maps to x plus 6 and y, or y plus 0. Let's do the same for number 2 now. Plot your points. Notice the C dropped from the top to the bottom. That's how I know this is going to be a flip. This flipped over the x-axis. So this is a reflection over the x-axis. Notice that all of the x coordinates remain the same. 2 to 2, 5 to 5, 4 to 4. They all remain the same. So the xy map to where the x stays the same, and the y all were multiplied by -1, or became the opposite sign. So we can call that negative y. It just really means the opposite y. The 3 transformations we learned prior all remain the same size. They did not change size. The transformation that we're going to talk about now, dilation, is where the object changes size. Keeps the same shape, but it changes size. We describe the size change with a scale factor. And a scale factor we call K. If we're changing something to be twice the size, that would be a 2K, or 2x, I'm sorry. 2 times the size. So example 1 I already know is a translation because I'm adding or subtracting to the x and y. Pause the video and try graphing it so we can compare. Here's my original image. Now I'm going to subtract 4 from every x value, and I'm going to be adding 1 to every y value. So I can find out my new coordinates and graph those. I've listed them before plotting them. So notice this image went to the left 4, that's what the -4 on the x means, and up 1 on the y. Positive, so it's going up. There's my description, translated left 4, up 1. This is what we saw in the warm-up. It's where the x is remaining the same. My xy is going to x remaining the same, and my y is becoming the opposite sign. So I can list out my new points now. So x remains the same, and y is becoming the opposite sign. If it was already negative, it would have become a positive on all these, but they're all positive, so I'm changing my y values to negative. And now I'm going to graph both of these, and it's going to be a reflection over the x-axis for my description. Notice my pre-image has my regular letters, and my reflected image has prime. So because I've memorized my transformations, I already know that xy being mapped to y negative x is a rotation 90 degrees clockwise. And I'll show you the chart that I've memorized from, and so you guys can do the same. If you're struggling with this concept, it's a little bit easier just to memorize it. Okay, and so what that means is that my y is going to be first, so my 0 is going to come first, and my x is changing signs. The negative x means changing signs, so -3 is going to become 3. Okay, for E prime, again, my y is going to come to the first position, so 3, and my -3 is going to become the opposite sign, so 3. C prime, the y is going to come to the first coordinate, and the -1 is going to become +1. And T prime, I'm going to put my y first, and my -1 becomes +1. Let's graph it and see what it looks like. Now you may be able to see that rotation 90 degrees clockwise a little bit better. And I know the last one's a dilation because I'm multiplying the x and y values by a number that's going to make it larger in this case. If it's being multiplied by a, not a fraction, but a number larger than 1, in this case 3, it's going to become 3 times the size for the x and the y. And so I'm going to take my values. This is a dilation with a scale factor of 3. So some people would write like k equals 3 in this case. And this k is different from the k right here. This k is just an ordered pair. And so what I'm doing is I'm taking each coordinate and multiplying by 3. So I get -6, -3, L prime, 3, -3. And n prime will be 3, -6. And let's graph this and see how it compares in size. Notice my pre-image is a lot smaller than my image. This table is how I know my transformations really well. So translation is pretty easy. It's when you add and subtract something. Reflections aren't too bad. It's where if you're reflecting over the x-axis, the x remains the same and the y changes. If you're reflecting over the y-axis, the y remains the same and the sign of the x changes. For rotations, they're a little bit more tricky for people to see, and so sometimes it's just easier to memorize these. Okay? 180 is not that bad. Both signs are changing, but the coordinates stay in the same position, so it just becomes -x, -y for rotation 180. But 90 clockwise and 90 counterclockwise are a little bit tricky for people. And k isn't too bad as well, because it's just something that we're multiplying by on a scale factor. The prior transformations that we learned about, reflection, rotation, and translation, is an isometry. It's a transformation that keeps the length, angle, measurement, and area. A rigid transformation is another name for an isometry. Dilations, on the other hand, will make the image be larger or smaller than the pre-image, so those figures are no longer congruent. And this is summarized for you in the chart below. Okay, for example 2, it says determine whether the figures are congruent. These can be really tricky, but what you want to see is the relationship between the pre-image and the new image. So like from -3 to -4, what's happening here? Well, this could be a -1. It could be subtracting 1. Let's check on the other x values. Yep, 2 to 1 is -1, 1 to 0 is -1. Okay, and then what's happening from 1 to -2? Well, that could be a -3. 3 to 0 is a -3, and 1 to -2 is a -3. So we're subtracting on the x values by 1, and we're subtracting on the y values by 3. And what type of transformation is this? If we have an xy mapping to this, well, this is a translation. And if it's a translation, are the figures going to be congruent? Definitely. The only one that's not going to be congruent is the dilation. And let's graph this so that we can compare as well. So pause the video, and when you're done graphing, compare to mine. We can see that the figures are congruent. Okay, in example B now, it's a little bit tricky because I'm looking at this and I don't see anything that I can add, like in the x I'm adding 1, but then I'm adding 2 and adding 2, so that doesn't work. And so I had to think about this one for a minute, but I can actually multiply 2 by 1.5. and 4 by 1.5, and this by 1.5. And I kind of noticed that because these were equivalent fractions. 2 over 3, 4 over 6, and 4 over 6 were all equivalent fractions. So I knew that I could multiply them by the same number to get from one to the other. And then looking from -2 to -3, let's see what's happening there. We're also multiplying by 1.5 there. Times 1.5 times 1.5 times 1.5. Okay, and so what this looks like is xy being mapped to 1.5x, 1.5y. And this is a dilation because I'm multiplying. It's actually going to become larger since I'm multiplying by a number bigger than 1. And let's graph this and see what it looks like. For example 3, let's graph the image, the pre-image and the new image. So there's really two transformations happening here, and that's confusing to see, but I can definitely tell that to go from A to P, this must have rotated at some point. But not only did it rotate, it looks like it had a translation as well. It slid in some direction. So I'm going to first take a look at rotating counterclockwise 90 degrees. Let's look at the formula for rotating counterclockwise 90 degrees. So here's our formula. So if I take all of the ordered pairs, A1 was 1, 2, and I make an A prime now. Well, if it rotated 90 degrees counterclockwise, that would be -y, so -2, and then keep the x value the same. It's just in the y coordinate spot. Okay, and b was 2, 1. So again, b prime, we flip, it'd be -1, comma, 2. And c was 4, 2, so c prime is going to be -2, 4. So now we can see that this translated down 1, 2, 3 spaces and 1 space to the left. So that would look like x minus 1 for the 1 space to the left and y minus 3 for the 3 spaces down. So if we use that mapping statement and we subtract 1 from all of the x's and subtract 3 from all of the y's, we will end up back at the, we'll end up to the final transformed coordinates. So -2 minus 1 is -3, and 1 minus 3 is -2. So this one works. -1 minus 1 is -2, and 2 minus 3 is -1. So Q works. And -2 minus 1 is -3, and 4 minus 3 is 1. So point R works as well.